In this video, I'll be doing one last example from the second law worksheet showing how we can apply the second law to solving numeric problems. So again, since we're dealing with the second law worksheet, we already know that we're likely going to be using that equation. So I'm going to go ahead and put it up in the three forms that we're used to seeing. First one being that net force is equal to mass times acceleration. That's the one we usually see when we talk about the second law. Second equation is just the same thing, just slightly rearranged. Now solved for acceleration. The net force divided by mass is equal to acceleration. And the last one will be solved for mass, so that we have net force divided by acceleration is equal to mass. Again, we're going to need to think of which of these equations is going to be the most helpful for us. And to do that, we'll need to look back at what we are solving for. What it's asking us for is the size of the unbalanced force. So again, unbalanced force, another way of saying our net force. And so since we're looking for the net force, we want to find the equation that is solved for net force. In that case, this happens to be the original form. Net force is equal to mass times acceleration. In order to solve this, we just need to find the mass and the acceleration based on the information that we're given and plug them in. So if we look for mass, we see that mass is up here, total mass of 6.94 times 10 to the 7th kilograms. So very large, so we shouldn't be surprised to see a very large mass there. And we multiply this by the acceleration. We're told that the general acceleration is supposed to be this value, the 0.191 meters per second squared. This might be a little bit harder to see because there are several numbers in this problem that aren't going to be related to what we actually need to solve. And so one thing that is helpful is thinking about units. We know that our mass should be in kilograms because that's the general SI unit that we use for mass. And we should expect to see the acceleration in something like meters per second squared. That's our SI unit, but any length per time unit squared could make sense here. And so that could be an indicator that the kilometers per hour, that 38 kilometers per hour, does not fit. We have a length unit divided by a time unit. That does not fit with an acceleration. So even if you're having trouble reading the problem, you can tell from the units that that's not going to make sense here. Now that we've got our values plugged in, we just need to go ahead and solve this. And what we'll find is that when we multiply this out, we are going to end up with a very large force, 1.3 times 10 to the 7th. And as for our units, we'll have kilograms multiplied by meters per second squared. And as we've talked about before, that combination of units is how the Newton is defined. This should give us our force in newtons, which is what we're looking for, and that should solve the question. So again, going back over our strategy, we thought about which equation would fit best with what we wanted. Since we're solving for the net force, we looked for the equation that had net force on the side of the equation. In other words, it was solved for the net force. We then had to find the appropriate values by reading through the reading through the question. And one thing that we saw was that even though there are several values in there, which can be confusing, only all of them had appropriate units for what we were looking for. We took the value in kilograms and the value that was meters per second squared, since those fit with the mass acceleration that we're looking for. Once we did our math and multiplying things together, the units do in fact come out to newtons, which is what we should expect, and that solved the question.